So as you know, the chain rule is critically important in derivative calculus. We have already talked about the chain rule in detail with respect to full derivatives. Now's the time for us to talk about the chain rule with respect to partial derivatives, where it's not that much more complicated. There's some interesting aspects to it, but once we understand how we can calculate partial derivatives using the chain rule, that will open a whole world of possibilities for us in machine learning. Okay, so let's say that we have a situation where we have these nested equations where u is a function of x and y is itself a function of u. And I'm using f and g to represent different functions. Recall that the chain rule for full derivatives in this case would be dy dx is equal to dy du times du dx, and the u terms just cancel out, so that we're obviously just left with dy dx. With univariate functions, the partial derivative is identical to the full derivative. So dy dx is equal to del y dx, which is equal to del y del u times del u del x. So with univariate functions, the partial derivative isn't very interesting, and I guess we should have expected that because partial derivatives are really designed for multivariate functions. So let's look at them over there. With a multivariate function, the partial derivative is really a lot more interesting. So let's say in this case, our inner nested function is u as a function of x and z. And f, let's just say for simplicity here, that y is just a function of u. So I find it helpful in these kinds of situations to draw this kind of tree diagram to show how these variables are related. So y is clearly dependent on u, and u is itself dependent on two variables, x and z. So it's a multivariate equation. So in this case, we have two partial derivatives. So we can chain y all the way back with respect to x and with respect to z. So the chain rule here is y with respect to x, so del y del x is equal to del y del u times del u del x. And so again, the u's can cancel out, and that gives us just del y del x. For the other side here, it's the same thing, but we're substituting z in for x. So del y del z is equal to del y del u times del u del z. And again, the u's just cancel out. And then going one step further, what if we have multiple multivariate functions? So now things get really interesting. So as one example, let's say we have y as a function of u and v, and then u and v are themselves functions of x and z. So in this case, x and z both are required to calculate u as well as v, and then y is dependent on u and v. So there are two partial derivatives that we can calculate here. So we can calculate del y del x as well as del y del z, but we need to take into account y's dependence on both u and v. So we use addition to add together these two different dependencies, these two different pathways. So to calculate del y del x, we do del y del u times del u del x to account for this side. And then to account for the bottom half, we use this term here. So del y del v and del v del x. For del y del z, it's a similar kind of situation, except you can drop in z wherever we had x in this first equation here. So it allows us to calculate y with respect to z via both the u and the v legs. Finally, generalizing the chain rule completely, we don't need to dig into this too much, but just so that you're aware of how the kind of logic that I've shown some specific examples for extends to any number of variables in our multivariate functions. let's say we have this variable y that is a function of any number of u variables, so up to m u variables. And then for each of those u variables, so let's call any given instance of these uj, it itself is a function of this multivariate function g, and g has up to n x's in it. So for I, from 1 all the way up to n, so for all of the x's, del y, del x whatever, del xi, say, is calculated by adding together all of the various individual legs. So xi is constant across here, and y is constant across here, but in between, we're changing u1, u2, all the way through to um. So there's your generalized expression of the chain rule. We'll tackle some exercises now to see if what I've been explaining makes sense.